1. Slow-motion earthquake. Scientists capture rare seismic event crawling beneath Earth's surface. 2. Underwater slow-slip earthquake recorded for the first time. Earth's hidden stress relief. 3. How Japan's seafloor sensors uncovered earthquake risks Türkiye can't see. 4. Silent earthquakes. Scientists track shock absorber phenomenon off Japan's coast. 5. Slow-motion earthquakes captured in real time, a breakthrough in seismology. 1. Slow-motion earthquake. Scientists capture rare seismic event crawling beneath Earth's surface. Imagine a quake that moves so slowly it takes weeks to travel just 20 miles. This is what scientists recently witnessed beneath Japan's Nankai Fault. A team from the University of Texas at Austin captured a rare slow-motion earthquake, offering a groundbreaking glimpse into how tectonic plates interact. This discovery isn't just a curiosity, it could revolutionize how we predict and prepare for seismic disasters. But here's where it gets controversial. What if the very forces that seem to calm the Earth's crust are actually hiding bigger risks? Let's unpack this fascinating story and explore why this finding has experts divided. The study relied on advanced borehole sensors, tiny but mighty devices drilled deep into the Earth's crust. Unlike traditional GPS systems, these sensors can detect movements as slight as a few millimeters, revealing secrets hidden beneath the ocean floor. The Nankai Fault, known for triggering deadly tsunamis, became the focus of this research. By tracking how stress builds and releases over time, scientists are starting to see patterns that could help us forecast quakes more accurately. But this isn't just about Japan. These findings could reshape our understanding of seismic activity worldwide. Here's the twist: the slow-motion quake acted like a shock absorber, easing pressure along the fault instead of building up to a catastrophic rupture. This challenges the old assumption that all tectonic stress must be released in one violent burst. However, some experts wonder if this slow release might actually mask larger, more dangerous shifts. After all, the Nankai Fault last erupted in 1946, causing widespread destruction. Could these slow quakes be a sign that the fault is gradually releasing energy, or are they just delaying the inevitable? What makes this discovery even more intriguing is the role of fluids. Researchers found that high-pressure fluids underground likely lubricate the fault, allowing it to slip slowly rather than snap violently. This supports a long-standing theory but raises new questions. How do these fluids form, and can we predict when they'll trigger a sudden shift? The implications are huge. If we can map these fluid-rich zones, we might identify areas where quakes are more likely to occur and maybe even intervene before they strike. The study also highlights the importance of long-term monitoring. These slow quakes take weeks to unfold, requiring patience and precision to study. For beginners, think of it like watching a glacier move. It's happening, but you need to observe it over time to see the big picture. This approach could transform how we design early warning systems, giving communities more time to prepare. But here's a thought: if we can't predict the timing of these slow quakes, how do we know when to act? As the research continues, one thing is clear: our understanding of earthquakes is evolving. The Nankai Fault's behavior reminds us that the Earth's crust is far more complex than we once thought. While this study offers hope for better safety measures, it also underscores the need for humility. After all, the planet has its own rhythms, and we are still learning to read them. What do you think? Do you believe slow quakes are a blessing or a hidden threat? Share your thoughts, because the conversation about earthquake science is far from. 2. Underwater slow slip earthquake recorded for the first time. Earth's hidden stress relief. What if the Earth's most terrifying forces had a secret, silent off switch? For the first time, scientists have witnessed this exact scenario playing out deep beneath the ocean, fundamentally changing how we understand the planet's most destructive pressures. In a landmark discovery, a team of researchers has captured direct, real-time evidence of an underwater, slow-slip earthquake. This isn't the violent, ground-shaking event we typically associate with the term. Instead, picture a zipper on a massive jacket being slowly and carefully undone. Along a major fault zone off the coast of Japan, two tectonic plates were observed gradually uncoupling, releasing immense built-up stress without a catastrophic bang. This gradual seismic event, tracked moving through a tsunami-prone segment of the fault, appears to be acting as a natural buffer, quietly absorbing pressure that could otherwise fuel a disaster. The findings, published in the esteemed journal *Science*, were led by researchers at the University of Texas at Austin. It's like a ripple moving across the plate interface, explained Josh Edgington, who headed the research at the University of Texas Institute for Geophysics, UTIG. Unlike sudden quakes that last seconds, these slow slip events unfold over days or even weeks. While only recently understood by scientists, they are believed to be a crucial part of the planet's stress management cycle, and these new observations from Japan's Nankai Fault provide the most compelling evidence to date. This incredible scientific leap was only possible thanks to a network of highly sensitive sensors embedded deep within the seafloor, right where the fault is shallowest. Damien Saffer, the director of UTIG, emphasized that these borehole instruments are technological marvels. They can detect ground movements as minuscule as a few millimeters, a level of precision far beyond the reach of conventional land-based systems like GPS. It's this ability to hear the Earth's subtle creaks and groans that allowed the team to catch this elusive event in the act. During the fall of 2015 and again in 2020, the team's instruments recorded a slow slip earthquake as it progressed along the fault's outermost section. Both times, the unzipping motion began roughly 30 miles offshore and was traced as it moved seaward over several weeks, advancing about 20 miles before fading away. But here's where the discovery gets truly exciting. For years, geophysicists have theorized that underground fluids might act as a lubricant, helping to trigger these gentle slips. The data from the Nankai Fault provided the first concrete proof. Both slow slip events occurred in zones where underground fluid pressure was unusually high, confirming that these fluids play a critical role in allowing the fault to release tension safely. This is profoundly important news for the region. The Nankai Fault is not to be taken lightly. It was responsible for a devastating magnitude 8 earthquake in 1946 that claimed over 1,300 lives and destroyed 36,000 homes. While another major quake is still anticipated in the future, this research suggests that at least one part of the fault, the shallowest section known for generating tsunamis, may be acting as a natural shock absorber, periodically and harmlessly letting off steam. And this is the part that should give everyone pause. The insights from Nankai are now being applied to other major fault lines, including the Cascadia subduction zone, which looms off the coast of the Pacific Northwest in North America. Here's the potentially alarming difference. While some slow slip has been detected deep within Cascadia, Safran notes that the tsunami-generating shallow end of the fault appears to be deadly silent. This lack of a natural pressure release valve could mean that this part of the fault is completely locked, building up strain for a future catastrophic, magnitude 9 level event. This raises a critical question about where we focus our scientific resources. The monitoring approach at Nankai has proven invaluable. Saffer argues that Cascadia is now a clear top priority area for this kind of high-precision observation to determine if it's quietly groaning or silently waiting for its breaking point. So, what do you think? Does the discovery of these safe earthquakes make you feel more secure, or does the silence of other faults like Cascadia worry you more? Should we be urgently deploying these advanced monitoring systems worldwide, even at great cost? We'd love to hear your perspective in the comments below. 3. How Japan's seafloor sensors uncovered earthquake risks Türkiye can't see. Imagine an earthquake so subtle it slips by unnoticed, yet reshapes our understanding of tectonic danger. Scientists just recorded one of these slow slip events off Japan's coast, revealing critical gaps in how nations like Türkiye monitor their seismic risks. Here's what this means for global earthquake preparedness. Silent shakers: how Japan's tech uncovers hidden earthquake dangers. New research published in Science reveals a groundbreaking find. 4 weeks, a slow-motion earthquake unfolded deep beneath Japan's Nankai Trough, a region infamous for deadly quakes and tsunamis. Unlike traditional earthquakes, this event didn't shake the ground. Instead, it acted like an underground pressure valve, releasing tectonic stress over 30 kilometers. The kicker: it was only detectable because Japan invested in advanced seafloor sensors buried nearly 1,500 feet deep, sensors Turkey lacks. It's like a ripple moving across the plate interface, explains Josh Edgington, a researcher who tracked the event using real-time data from borehole sensors. These instruments catch movements too faint for standard GPS networks, offering insights into how faults behave under pressure. The Nankai Trough has left a trail of destruction. The 1946 quake killed 300+ people, and another slow slip happened there in 2020. Both started near the coast and migrated outward, a pattern researchers now call a shock-absorbing mechanism that might reduce sudden rupture risks. But here's the part most people miss: this discovery isn't just about Japan. It's a wake-up call for places like Turkey, where critical fault systems lie offshore and remain unmonitored. Turkey's blind spot: why offshore monitoring matters. Turkey's North Anatolian Fault, NAF, has been a seismic time bomb for decades. It's the boundary between the Eurasian and Anatolian plates, racked by horizontal strike-slip motions. Since 1939, deadly quakes have marched westward toward Istanbul, including the 1999 Izmit disaster that killed 17,000+. Today, USGS warns of a 62% chance of strong shaking in Istanbul within 30 years. But while researchers model urban risks, like neighborhood resilience scores, they are ignoring a blind spot: the Marmara Sea. You'd need 10,000 magnitude 5.1 quakes to match the energy of Turkey's 2023 disaster, notes geologist Kevin Stewart. Yet current models focus on land, skipping vital data on offshore faults, fluid pressures, and submarine landslides. For example, the 2025 Istanbul study used 28 indicators but omitted tectonic stress patterns under the Marmara Sea. Without offshore sensors like Japan's, Turkey can't detect slow slips or changes in fluid pressure that might signal an impending rupture. And this is where the controversy arises: should nations prioritize costly offshore monitoring when urban areas already face immense risks? The answer hinges on history. Turkey's coastline has seen over 80 tsunamis in 3,000 years, often triggered by moderate quakes. In 1509, waves breached Istanbul's walls. In 1894, a surge flooded coastal districts. Professor Sukru Ersoy warns that a 6.5 quake in the Marmara could trigger landslides, creating tsunamis with no early warning system to alert residents. The debate: are offshore sensors worth the investment? Japan's approach, deep-sea observatories, isn't common. Even Cascadia, the subduction zone threatening the U.S. Pacific Northwest, lacks similar systems. Criticisms often focus on cost, but proponents argue it's cheaper than a prevented disaster. Cascadia and Turkey are top priorities for this tech, says Dr. Damien Saffer, a Texas geophysicist. The Japanese model proves monitoring works. Yet implementation faces hurdles. Turkey's researchers collaborate with international teams on paleoseismology, studying ancient sediment to trace tsunami origins, but real-time data remains elusive. The 2025 study proved slow slips release energy gradually, not violently. This challenges old assumptions: faults aren't either locked or rupturing, they have middle ground that land-based systems miss. Rethinking earthquake preparedness. So what's next? For Turkey, the path forward involves merging Japan's tech with existing urban models. By combining borehole data with resilience scores, scientists could predict where infrastructure gaps, like low emergency access in Isenla and Gungoren, align with hidden offshore risks. It's a complex puzzle, but one that could save lives. But here's the critical question: will Turkey act? As Istanbul's population grows, the stakes rise. The Japanese example shows monitoring isn't just about early warnings, it's about rewriting our understanding of danger. The real challenge isn't just installing sensors, it's convincing policymakers that silent shakers matter as much as shaking ones. Now we want to hear from you: should high-risk regions prioritize offshore monitoring, even if it diverts funds from urban preparedness? Share your thoughts in the comments below. 4. Silent earthquakes. Scientists track its shock absorber phenomenon off Japan's coast. In a groundbreaking development, scientists have successfully tracked a mysterious undersea event, shedding light on a phenomenon that has long eluded researchers. But what exactly did they discover, and why is it so significant? Prepare to dive into the depths of this scientific enigma. The elusive silent earthquake. Imagine an earthquake that moves in slow motion, exerting pressure on the Earth's crust without the usual violent shaking. This is the essence of a slow slip, or silent earthquake, a seismic event that has puzzled scientists for years. In a remarkable first, researchers from the University of Texas at Austin have captured the motion of one such earthquake along a major fault zone on the ocean floor, just off Japan's tsunami-prone coast. But here's where it gets fascinating: this slow-motion earthquake was behaving like a shock absorber, gradually releasing tectonic pressure as it moved. The team's observations, published in the prestigious journal Science, provide a unique insight into these enigmatic events, which are distinct from the more commonly known slow rupture velocity earthquakes that can trigger tsunamis. Unzipping the fault line. Dr. Josh Edgington, a key researcher, described the phenomenon as a ripple moving across the plate interface. These slow-slip earthquakes, as they are sometimes called, release energy over extended periods, from hours to months, and are not truly silent, but very quiet. The team's sensors, installed near the shallow reaches of the fault, were able to detect these subtle movements, a feat that land-based monitoring technologies often struggle with. A breakthrough in seismic research. The significance of this discovery cannot be overstated. By tracking these silent earthquakes, the researchers have potentially unlocked a way to better understand and manage seismic hazards. The Nankai Fault, where the observations were made, has a history of major seismic events, including a magnitude 8 earthquake in 1946 that caused significant loss of life and property. The team's findings suggest that slow-slip earthquakes may help dissipate energy in these areas, particularly at the shallow end of the fault, reducing the risk of devastating tsunamis. The role of fluids in seismic activity. Another intriguing aspect of this research is the role of fluids. The scientists found that both of the slow-slip earthquakes they observed were accompanied by higher-than-normal fluid pressures in the Earth's crust. This supports a long-held suspicion among seismologists that fluids play a significant role in driving slow earthquakes, although this idea had not been confirmed until now. Implications for the Pacific Ring of Fire. The implications of this research extend far beyond the waters off Japan. The team's findings could help refine earthquake and tsunami hazard models for other regions along the Pacific Ring of Fire, including the Cascadia subduction zone off the U.S. Pacific Northwest. This area, known for its potential to generate magnitude 9 earthquakes and deadly tsunamis, could benefit from the high-precision monitoring approach demonstrated in this study. A new era of seismic understanding. This research opens up a new chapter in our understanding of seismic activity, particularly in undersea environments. By tracking these silent earthquakes, scientists can now better predict and manage the risks associated with these events, potentially saving lives and reducing the impact of future disasters. And this is the part most people miss: the quiet, slow-motion earthquakes may hold the key to unlocking a safer future for those living in earthquake-prone regions. So, what do you think? Are these silent earthquakes the key to a safer future, or is there more to the story? The debate is open, and your thoughts are welcome. Perhaps the real controversy lies in how we interpret and act upon these fascinating discoveries. 5. Slow-motion earthquakes captured in real time, a breakthrough in seismology. Picture this: scientists just witnessed geological events unfolding in slow motion deep beneath the ocean, a breakthrough that could revolutionize how we predict deadly earthquakes. But here's where it gets controversial: could this technology actually give false confidence in quake-prone regions? Researchers from the University of Texas Institute for Geophysics achieved a scientific first by capturing slow-motion earthquakes in real time using specialized underwater sensors. These events, technically called slow-slip events, SSEs, unfold over days or weeks rather than seconds. Unlike violent traditional earthquakes, SSEs release built-up tectonic pressure gently. Think of them as Earth's natural shock absorbers. Teams monitored 2 SSEs near Japan's Nankai Trough, where the Philippine Sea Plate slides under the Eurasian Plate. Using advanced borehole sensors placed directly on the seafloor, they detected ground movements as subtle as millimeters. What they found confirms a critical theory: these slow quakes significantly redistribute stress along fault lines, acting like geological pressure valves. Here's the fascinating part: these slow quakes may be linked to underground fluid pressures, and the upper fault sections can relieve pressure independently. This discovery is especially vital for the Pacific Ring of Fire region, where the Nankai Trough has historically unleashed devastating tsunamis, like the 1946 quake that killed over 1,300 people. The research suggests areas like Japan benefit from this tectonic cushioning. But here's the twist: other dangerous zones like North America's Cascadia subduction zone completely lack this protective mechanism. As geophysicist Damien Safra puts it, is the fault near the trench deadly silent? This stark contrast forces us to ask, should communities near silent faults like Cascadia live under constant threat while others have early warning systems? Some argue this creates unequal disaster preparedness globally. While earthquake prediction remains imperfect, incorporating SSE data into models could save thousands of lives. The technology behind this breakthrough, detecting once invisible geological whispers, represents a seismic leap in our understanding. Yet we must confront an uncomfortable reality. Even with advanced monitoring, can we ever truly predict the big one? What's your take? Should governments prioritize this monitoring despite the uncertainties? The debate is just beginning.